One of the first concepts that we are going to have to be able to understand and to differentiate between is the concept of distance versus displacement. They're very similar, they're very easily confused, but in order to show the difference, let's consider the following scenario. Let's say you have two runners, the red runner and the blue runner, and they're going to run along this straightaway one-dimensional path. So let's say the red runner runs, I guess, maybe 80-90% of the track, and the blue runner only runs about 50%. If you were asked who ran farther, I don't think hopefully this would be too difficult. I think most people would probably think along the lines of, well, if we represent how far the red runner went with an X versus how far the blue runner went with a Y, we can kind of see visually that X is greater than Y, therefore the red runner ran farther. Seems straightforward, so why the distinction in these two terms? Well, that becomes apparent when we view another scenario. This time, the two runners will be running in a circular track. Once again, let's say the red runner completes the full course and the blue runner only runs about, let's say, maybe 50% of that lap. If I were to ask again who ran farther, well, now we might run into a problem because we'll likely get two different answers. We'll get some people who do the same thing we did before, and they say, well, the path that the red runner took, we'll call that X, and the path that the blue runner took, we'll call Y. And clearly X is larger than Y, therefore the red runner ran farther. And that would be correct. However, others may point out the fact that the red runner actually didn't go anywhere. He spent a long path to end up exactly where they started, and they actually have not gone any farther than where they started. In that case, if we call how far the red runner went from their starting position, A, which is really no change, and we draw a straight line, that orange arrow there, to represent how far the blue runner ended from where they started, and we call that B, well, you can clearly see that B is in fact larger than A. The blue runner has actually moved farther away from where they started than the red runner did. So in that case, we could conclude that the blue runner ran farther. So here's where we have a little bit of an issue because we have two different answers to the same question. Now, the way that we get around this is to hopefully understand that the word farther is no longer acceptable within physics. It's too general. We need to be a little bit more specific. If we want to be more specific, we should really figure out whether we are asking who ran a farther distance or who ran a farther displacement. So to define distance, to give us something to work with, I think an easy way to say that would be the length of the total path taken by a moving object. So if we assume that dotted black line represents the motion completed by some object moving from A to B, the measurement of that entire path, kind of just tracing it along with our finger, that would be the total distance. Every single step or meter that this object moves, you add on to that total distance. Distance in physics uses the standard unit of meters. Probably seems fairly straightforward. That's probably what you were thinking already. Displacement is what throws some people off. Displacement is not the actual path taken. It is the length of the straight line between the starting and the ending point of a motion. So if we take the same motion from the previous example above, we represent the motion of whatever this object is with the black dotted line. The black dotted line, if we were to actually trace it, would be the distance. The displacement is just the straight line distance, or straight line measurement between A and B. It is not necessarily the actual path taken by the object. It is simply how far the object has been displaced from where it started. How far did it end from where it began after it completed its motion? Now, the reason this can be a little bit tricky is because it's a measurement that doesn't actually necessarily represent the motion that the object took. Why does that become important? Well, something like distance is probably important if you want to maybe analyze the wear and tear on the tires in your car, right? We can't just say, well, I park it in the same spot in my driveway every day, so those will last forever because they have no displacement. Well, the distance is going to wear those car tires down. Displacement is more useful in physics because it allows us to figure out where objects are going to end up, where they're going to be, regardless of the motions that they're taking. For that reason, the unit for displacement is still meters because you're still measuring, a length of some sort, but it's a meters plus a direction. It's very important you need that directional component. 25 meters is an example of distance. 25 meters north, for example, is a sample displacement. What is all this talk about direction? Well, it really comes down to the types of quantities that we're going to see in this course. And the two main types are going to be scalar quantities and vector quantities. Scalar quantities are any quantities in which no direction is required to give the measurement meaning. Now, that's not really helpful, but if I provide some examples, maybe I can clarify. So scalar quantities are things such as age, temperature, money, height, volume, etc. If someone asks you how old you are, you may say 16, 17. You don't say 16 years old south or 19 years north, 14 years up. That doesn't really make sense. You don't need a direction for that measurement to make sense. You're used to dealing with scalar quantities because most of what you deal with in your day-to-day life are scalar quantities. The directional component isn't even a factor. Unfortunately, in physics, we do use some scalar quantities, but we tend to use vector quantities much more, and those are quantities for which a direction is required to give that measurement meaning. So one of the examples I like to discuss would be, imagine I bet you $1 million. I handed you a tennis ball and I bet you $1 million that you couldn't close your eyes and throw that tennis ball and hit me with it. But the caveat being, I'll tell you how far away I'm standing. So you close your eyes, I hand you the tennis ball, I tell you I'm going to be 10 meters away from you. You throw the ball, you miss, you open your eyes, I'm not even in the classroom. I've actually climbed on the roof of the building, but I am technically 10 meters away from you, just above your head. So telling you that I'm 10 meters away from you doesn't tell you where I am. It gives you kind of like this sphere of possibility. I could be 10 meters in any direction, up, down, left, right, diagonally. But in order to understand more precisely where my actual position is in space, I would need to tell you 10 meters vertical, 10 meters north, something along those lines. These samples that I'm going to use here, because they tend to be physics examples, are not necessarily going to be everyday things. But displacement, as we just learned, because that direction is important, is a vector quantity, as are things such as velocity, acceleration, force. Most of the vector examples are unfortunately quantities that we will be studying in this course because physics relies heavily on them. But for right now, just understand that if you are a scalar quantity, you don't need a direction. Providing a direction literally makes that measurement confusing, like age. And if you have a vector quantity, which unfortunately we have a lot of in physics, you need that directional component because you need to know which direction that object's going to move in, or is it going to speed up or slow down? And all of the answers to those questions are going to come to understanding these vector quantities.